In the last video, we introduced the idea of differentiation, measuring the slope of a function. In this video, we introduce a small piece of notation that is used when we are calculating the slope of a function of multiple variables. Explicitly describe function f by writing down an association rule in terms of variables a and b. We can potentially calculate a variety of slopes by exploring the horizontal plane along different directions. We can hold a constant while varying b, vary a and b together, or instead vary a while holding b constant. The change in vertical height of f can depend on the direction in the AB plane in which we choose to wiggle. It is helpful to introduce language that lets us specify directions in the AB plane along which to calculate the slope of f. To this end, we introduce the curly d symbol called a partial. The partial refers to a derivative taken along one of the variables explicitly written down in the association rule, while holding all other variables in the association rule constant. The variable from whose heights a slope is to be calculated appears in the upper part of the symbol, and the variable along which these heights are to be compared appears in the lower part of the symbol. For example, the symbol partial f partial b specifies the slope calculated by holding constant a, which would otherwise be variable, while jiggling b. In the same sense, the symbol partial f partial a refers to the slope calculated by jiggling a while holding b constant. An equivalent way to describe partial f partial a follows in equations. Hold the value of b in the function f on a comma b constant somewhere. Let's call it b sub 0, b naught. Let's call this object f sub a comma b naught on a, which is a single variable function, a function of a alone, so it is distinct from f on a comma b. The things in the parentheses for these two creatures are different. A by itself is distinct from a comma b, so the creature f sub a comma b naught on a is not the creature f on a comma b. The derivative of this new object f sub a comma b naught with respect to a is denoted by partial f partial a, parenthetically with b held at b naught, though the location b naught is often suppressed in notation. Because we explicitly said that f was a function of a and b, the variables held constant or allowed to jiggle in these examples were unambiguously specified by the symbols partial f partial a and partial f partial b. We provide an example below of a situation in which clarity is important, yet where habits common in physics can cause confusion. Suppose we are studying a function f on L, r, where L is the variable that goes into the left slot and r is the variable that goes into the right slot of f open parenthesis blank space comma blank space close parenthesis. Suppose we also know that the variable that should be deposited into the left slot is a function of time a on t, and that the variable that goes into the right slot is a function of time b on t. Let's give a name f sub capital T to the new composite function that is the combined set of instructions that first use t to get intermediary values for a and b, and then second place those intermediary values for a and b into the left and right slots for f respectively in order to get a single number out from f. This composite set of instructions is not the same as f, so it is best to label it distinctly, for example as f sub capital T. F sub capital T is a single variable function, a function exclusively of t, while f itself is a multivariable function of L, r. L, r is distinct from t. The two functions eat different things. F sub t is not f. The words we are speaking sound reminiscent of the words we spoke on the previous slide when we defined the partial derivative using equations. This is because on both that slide and this one, we are constructing a single variable function by starting with a function of multiple variables. On the previous slide, we obtained a single variable function by holding one of the variables in one of the slots constant, pretending in a sense that it was not a variable. On this slide, we obtained a single variable function by making the stuff in the slots dependent on a common variable, so that the overall composite function was, in the end, a function of a single variable. Explicitly describing related but distinct functions, as we have done on this slide, can make it easier to understand equations in which they appear simultaneously. For example, we may wish to state that the derivative of the single variable function f sub capital T with respect to time t equals the partial derivative of a different function f with respect to its left slot multiplied by the derivative of the function a with respect to t plus the partial derivative of the function f, again not f sub t but instead f, with respect to its right slot, multiplied by the derivative of the function b with respect to time. Compare this format with the style most people use to write down the same idea. They reuse symbols all over the place to mean slightly different things that are just similar enough to be confusing. This equation is read derivative of f with respect to t equals partial derivative of f with respect to a times derivative of a with respect to t plus partial derivative of f with respect to b times derivative of b with respect to t. People conceal fine print. Yours truly is no different in this regard. Throughout the tutorials, the compact style in the bottom equation is used, so the viewer may need to pause videos to unpack notation using pencil and paper during the first several encounters, until the detailed discussion implied by such terse equations becomes ingrained.